Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today I'm pleased to welcome Dennis Craggs. Dennis studied at the University of Detroit and Wayne State University, achieving a master's in engineering mechanics and operations research. He's a licensed professional engineer and a quality and reliability engineer. In various roles at NASA, Teledyne CAE, Ford Motor Company, and Chrysler, he worked in fluid mechanics, heat transfer, mechanical and electrical design, test and development, and computer programming. At NASA, he supported engineer test and development activities. At Teledyne CAE, Dennis designed axial and centrifugal compressors for cruise missile engines. At Ford, he worked in chassis engineering component design, and in the Ford Computer Center, where he created relational database software to store engineering test data, provide an easy graphical user interface, and statistically analyze the results. At Chrysler, he was a statistical specialist and assisted managers and engineers in the development of performance specifications and validation standards for mechanical, electrical, and powertrain automotive components, analyzed verification test results, and assessed supplier readiness for manufacturing. He developed statistical methods and software to graphically analyze warranty trends using Weibull methods and project future risk. Over the last few years, he developed methods to statistically analyze massive vehicle telematics databases to characterize vehicle lifetime usage. As a member of a joint USA SAE and German SVEI task force, Dennis supported the development of SAE J1879, Handbook for Robustness Validation of Semiconductor Devices in Automotive Applications. Representing Chrysler to USCAR, he helped to develop the automotive lead-free electronic validation standard USCAR 40, lead-free solder validation test plan. In addition to all that, Dennis has taught graduate-level statistics and reliability at Wayne State University and provided an introduction to Minitab training seminars to corporate clients. He presented at the Society of Automotive Engineers, the American Society for Quality, the Automotive Electronics Council, ISAT conferences, and authored SAE and ISAT technical papers. Dennis, welcome, and thanks for joining us.
Hi, Tim. Thank you very much for this opportunity to talk to you and the audience.
So, Dennis, your work obviously with vehicle telediagnostic data and big data generally seems very relevant today, especially with all the interest in the Internet of Things. Can you give us some perspective about what kind of data is available and specifically how that's been used to address reliability issues?
Well, right now there are several very large data sources. One is you could take surveys. National Highway Traffic Safety Administration has customer surveys that they do a lot of statistical analysis to characterize how people use their cars. But more focused are some of the company-sponsored surveys in their different marketplaces. For instance, they may survey audiences in China. How do they use their cars? Another big data source is warranty data. There's a lot of information collected every time a vehicle goes in for some kind of warranty service that the company pays for, including like the miles, the time, the date, and the serial number. All this gets connected back to when the vehicle was produced and sold and things like that. And so you can do a lot of big data analytics on that kind of data, and that's a very large database. Recently, though, the newest thing has been what I would call telematics, and we called it within the auto company telediagnostics. Mm-hmm. But telematics is basically where there's a module installed in a vehicle with the owner's knowledge and permission, and it collects information from an electronic bus called the CAN bus that communicates what's information between all the modules. Well, this can also be captured and then sent back to a data collection supplier, and that's basically what I call telematics data. So that's the raw data, and it can get to be really huge. for instance, a single police vehicle had they were monitoring the CAN bus about once per second, and would gather upwards of 150 channels of information.
Wow.
That vehicle was used 7 days a week, 24 hours a day, because they were running it almost continuously, multiple shifts. And what happened is, at the end of slightly over a year, there were 22 million records of 150 channels that could be used or could be extracted.
That's a lot of data. Dennis, do they do any buffering to try to, I don't know, average that data?
Well, the buffering was done storing the raw data at that point. But when the buffer got too big, it would have to communicate that back you to a data collection source. That effort was not totally successful because some data was dropped because you might not be near a receiver to be able to transmit the data. I believe they were using Wi-Fi when Wi-Fi was free, but eventually people were asking for passwords.
Gotcha. This, for some reason, Dennis, I was just remembering. It seems like there was a commercial for an insurance company not too long ago where they were also trying to capture data from vehicles in operation. Does that ring a bell?
Yes, I think it was Progressive Insurance. I believe that was a company, and they would put a module onto a vehicle. They would again plug it into the CAN bus, and I believe it had accelerometers and could record various things from the relating to vehicle performance. And for that benefit, the customers were, or for that functionality, or for that, I'm stumbling over my words. To entice a customer to do that, they would give them a discount on their rates.
Sure. Dennis, can you give us a feel for what kind of data is being collected? I mean, there's a lot that you could pull off the CAN bus, right?
Oh, yes. Let's say you could pull off various kinds of counting data, such as how many starts did a vehicle go through. So every time a record came through, it would have, and this was not the most efficient way to do it, but it would have like a start number on it, like how many times was it started. So over a period of time, you could, looking at how that number changed, you could determine how many starts were in a particular day, how many were in a year, and so you could tell how many trips a vehicle would be, or not trips, how you could tell how many engine starts the vehicle experienced.
Gotcha.
And then you could compare those numbers across a whole population of vehicles that you may be interested in analyzing, and determine some kind of a distribution. So you could determine what would be a large number and what would be a small number, what would be a typical number. And we would, one way to do this statistically is to characterize a 5th percentile, a 50th percentile, and a 95th percentile kind of usage.
Got it. That makes a lot of sense. I don't know if you can give us an example of how this kind of data has been used, maybe in design and to help improve, I don't know, starter design or something like that.
This kind of data was used in a new type of vehicle feature called stop-start vehicles.
Yeah, sure.
And stop-start vehicles would turn off the engine when it came to a complete vehicle stop and certain other conditions were met, okay?
Right.
But they wanted to understand how a stop-start vehicle would be functioning. So in this case, now there are more engine starts than there are trips, so they would monitor.
Right.
So we would characterize that. Now, how many trips would a vehicle go through? Well, the trips would be a typical vehicle could have 400,000 engine starts. I'm just pulling the numbers off the top of my head, but the number of I'm sorry, repeat that. I have to repeat that. It was about 270,000 stop-start events, because not every one was countable. For instance, you could start an engine, and a vehicle would be sitting there. You wouldn't really be moving, so those would be stop-start trips.
Right. Like we've been saying, there's just a huge amount of data that's available out there. In fact, one of the things that I've heard people say is that we're basically drowning in data.
Yes.
And what's missing, is the ability to make sense out of all of this. How can designers and reliability engineers work together, to make sure this data is actually useful in improving reliability?
Okay, that's the interesting thing. We're drowning in the data. How do we use it? Well, first of all, we have to focus at what is the issue at hand. What is the particular engineer worried about? Like I said, there could be 1,000 channels of information on a vehicle. When I did this study on police, it was 150 channels. That was about
Wow.
5 years ago. Now they're up to about 1,000 channels on the bus. And so focus is important. How do you eat an elephant? One bite at a time. So what channels am I interested in? If I'm looking for the distribution of vehicle speeds, I should be looking at a vehicle speed channel.
Right.
So I've immediately cut it down by a factor of 1,000.
Good point. Yeah, that's a huge help right there. Are there have you seen situations where reliability engineers have actually been involved in helping to design these data collection systems where there's a specific kind of data or information that they need, and so they help put the appropriate sensors and collection systems in place?
Well, yes. In general, when a module is being installed in a vehicle, there's, of course, this long list of potential channels that could be monitored.
Right.
And the engineers usually would submit a request for that information. Sometimes the data might not be directly measured, but for instance, it might have to be calculated from some of the other parameters that are in there. When you have, I'm trying to pull up in my mind an example, but for instance, if you wanted to calculate the torque on a particular gear, you'd have to throw in other information like what is the gear that you're in, because there are different gear ratios and that affects the torque that's being transmitted to the gear.
Sure, that makes sense. It seems like a lot of this data is being kind of collected at a macro level, if you know what I mean.
Oh, yes.
But as the sensors become smaller, cheaper, more prevalent, that we have the ability to collect data at lower and lower levels in these subsystems.
Well, there's another factor at work. There are tougher requirements coming in every year, usually due to regulatory agencies demanding information or demanding different functionalities. So more and more information is going on the CAN bus. So that's one thing that has driven the number of channels being monitored from about 150, which was about 5 years ago, to about 1,000 right now.
Right. I guess one of the things that's kind of exciting or interesting to me is this idea of reliability engineers, again, helping to starting out with specific questions that they want answers to, and then helping to design the systems to be able to collect the data, to help them understand what's going on.
Yeah, I've worked with a lot of the individual engineers on these projects, and sometimes, the questions were at a fairly high level, so we could look for basic information that was always being collected. Like, for instance, we would always collect the vehicle speed. We would collect the engine speed. We'd collect the information on what gear the vehicle in. These are macro levels that are really very important. There were some things that, they were like accelerometers that they may not have had sufficient resolution because you're lunching off of non-dedicated sensors. But for engine speed, engine torque, those are sufficiently important that there was good data on the bus.
Des, I want to shift a little bit here. We've been talking about the data, but I want to ask you a little bit about the analysis side also. So, we talked a little bit about your work with Minitab earlier. I wonder if you could tell us a little bit about some of the things that are happening on the analysis side that are designed to help engineers figure out what to do with all this data.
Well, first of all, with the big data analytics, there was very little that was available from an analytic perspective when I first got started. The, for instance, you might look at a million records and you could gather some statistics on it, like what's the average, what's the standard
Sure.
deviation, but that does not put it into any kind of perspective, especially if you wanted to compare 15 or 20 vehicles or 100 vehicles. You really need different methodologies. Also, you have to compensate for different amounts of usage. Some vehicle in the database could have a month of data. Others may have 2 years of data. If you don't do some kind of standardization, the individual vehicle that had 2 years of data will overwhelm any data from the vehicle that had 1 month of data.
Right.
So we need to go through some kind of standardization first. Then it's a question of what kind of statistics. So I basically took the philosophy that a picture is worth 1,000 words and developed some graphical methods to capture the data from the fleets. For instance, there is a distribution of vehicle speeds that every vehicle would be experiencing. Now, most of the time, the engineers would use what they call um, interval frequency distribution. It's a PDF basically, and I changed it to a cumulative distribution, so you could see the total pattern going up to 100% for each individual vehicle. And then you overlay them one on top of the other, and you could see which was a severe vehicle usage and which was not. So you're looking for patterns.
Sure. Yeah, I think that's a very good point. I mean, reliability engineers are typically trained in statistics. I mean, they know how to do the basic, mean and standard deviation and all that. Maybe even some hypothesis testing. But when you've got this much data, it's sometimes, like we said before, it's kind of hard to figure out what it's telling us. It almost seems like we need. What's the word I'm looking for? Kind of predictive capabilities, pattern recognition. Are these kinds of things starting to be used with this kind of data?
I don't know about pattern recognition. I'm not an expert in that area. My expertise more goes toward engineering and statistics and programming.
Sure.
So what I've done is use those three skills to develop tools that could be applied in many different situations. So I developed basic tools for counting situations like trips per day, things like that, or analyzing parametric data that is more continuous, like vehicle speeds, engine torques, and then two-dimensional or multivariate information like engine speed, torque, and gear type of situations.
Right. Dennis, we've been talking about the automotive industry exclusively. I know you do some consulting work elsewhere as well. Are there some other industries that are really in a good position to benefit from this same kind of approach?
I could see the Internet of Things would be a future beneficiary. For instance, they're talking about having your let's say control of your refrigerator or something like that. Knowing or control of air conditioning in your house from your smartphone or security systems. All those could benefit. For instance, if I'm looking at my refrigerator or let's say I'm a refrigerator designer, I may want to know how frequently the door is open because that may affect how I want to test the door for durability.
Good point.
If it's running, how much power does it consume? How many times does it turn on that motor to start the air conditioning? I mean, the refrigeration cycle. Those things would lead to us to methods to improve testing of the motors.
Right.
And that makes sense. That's the whole focus I've had is how to get better information to the design engineer so he can target better, create better tests that target his product.
That sounds great to me. Boy, that's exactly where we need to solve these problems is at the design level. That makes a lot of sense. Dennis, you've been talking a lot about your consulting work, but you've also been doing a lot of teaching, like at Wayne State University.
Yes.
I wonder if we could get your perspective. What should reliability engineers be learning about data analytics to prepare them for this new world? I mean, beyond just taking basic statistics.
Well, that was what I was going to start with, basic stats, because we have to understand, have a foundation on which to build the knowledge or understand more complex knowledge, complex statistics. Um, so, for instance, I would focus a lot on, I've used them in my plots, is understand what's a cumulative distribution. We're trying to understand the variation from one customer to another, and to characterize that variation. So I would say probability distribution plots of many different types could be a topic. And then understanding the graphics that are associated with this with the plot. In other words, from a graphic, you could pick off a 5th percentile, a 50th percentile, a 95th percentile, or even if you have enough data, you could extrapolate to a 99th percentile, although that would be, you'd have to have quite a bit of data to do that. But you can get a rough measure for what is the individual, what different, how you can characterize a population.
Gotcha. That makes sense.
And an example, you can also capture data, for instance, just providing a very simple example. I was looking at vehicle speeds and a distribution of vehicle speeds, and from that you can tell how much time a vehicle is idling. In other words, it's time when you've been collecting data and the engine is still running. So how much time is a typical vehicle idling? Well, it's in the neighborhood of around 20% plus or minus some tolerance. How much time does a police vehicle idle? Now, we think that's a lot more, but how do you put a number to that? And well, it turned out that it was, from the data I had seen, it was about 66% of the time they're sitting there idling and their car is not running.
Wow, I had no idea.
Well, the reason for that is that when they're on a shift, they are they do not turn off their vehicles, the police cars, at any point in time. If they make a stop, the vehicle is still running. If they're in having lunch, the vehicle is still running, because they have to turn on all their electronics and boot up all their electronics during the day. Or, I mean, if the vehicle stops, they lose power, they have to reboot.
That makes sense. That's interesting. Well, Dennis, it's been great talking with you. Thanks so much for joining us today.
Great. I'm glad. I really appreciate this opportunity to share what I've been doing.
That was Dennis Craggs, principal at Dennis L. Craggs, LLC, an independent reliability consultant, analyst, and trainer. This is Tim Rogers. Thanks very much for joining us.